Yeah, so we'll start with some theory parts, just what we left off with last time, and then we'll just go straight into sort of the workshop parts, and we'll get everyone set up and running. So the first bit I want to talk about is some SIMD things. So SIMD stands for single instruction multiple data, and specifically we're going to talk about like hardware vector instructions. So sort of modern CPUs have wider registers, so they can process data in parallel in a single instruction. So if you remember from last time, a register is just some temporary memory storage within the CPU itself. And these sort of modern registers can be, for example, 256 bits wide. And if you have that much space to store some data, you can pack multiple numbers together into a single register. And the reason we do this is because going to get data from memory has a high latency cost. So if you can do it all in one go, then you can only pay that cost once for four numbers or 8 numbers, depending on how many bits each of your numbers have. Along with just having these registers, there's some special hardware built into the CPUs themselves that let you process that information at the same time as well. So just like we were talking about last time, if you load, for example, 2 integers into the CPU, it has some special hardware that will perform that calculation in 1 clock cycle. So so it's unit of time in the CPU's frame of reference. So this is a sort of hardware level parallelism. So you basically can get this extra performance for free with a little bit of code. So the main sort of example of this is doing like vector addition. So for example, if you have a vector X and you want to add it to a vector Y, we do this addition element wise. So the calculation of the first element, X1 plus Y1, is completely independent of the second element, X2 and Y2. So it doesn't matter what order we do this calculation in, and we can even do them at the same time. And if we can do that, then we can achieve a speed up. So instead of having to do 2 additions, we can just do a single addition and do them at the same time. So yeah, basically all of this is, there are some special operations that you can use or instructions that let you do these in parallel. So some of these instruction sets, you may have seen these sort of acronyms before. So there's SSE, which is streaming SIMD extensions. This is for the x86 processors, so pretty much everyone here will be using x86, apart from some people using the new MacBooks, which are ARM-based. But this is quite old, so this is like early 2000s. They sort of started adding these onto processors. And more recently, in sort of 2010s, they've started adding AVX to a lot more instructions, and they're basically just more complicated instructions and also larger registers as well. So you can only do this like hardware level parallelism if you have the actual processors that support it. So online you can check what processor you have, and there should be a section saying all of the instruction sets it supports, and you might see this SSE and AVX. However, they're usually limited to the sort of higher end processors. So if you have like a notebook processor, it might have SSE, but it might not have AVX. So if you're wanting to use this in your own code and you might not see any speedups by using these, it might be because these instructions just aren't supported on your CPU. So just as an example, on the left we have some code written in Julia, which just sums up numbers in an array. I won't go into too much detail here. Hopefully the code is readable enough for everyone. The nice thing about Julia is you can very easily add vector instructions to your code. So you don't actually change too much. You can use a macro. So you can see on the front of the for loop, we've added this @SIMD symbol. And a macro is a sort of metaprogramming technique. And metaprogramming is just writing code that writes more code. So the macro takes as input this for loop written in the source code, and it will produce some more code to translate all of the addition operations and all of the iteration through your array into the vector instructions. that make sense? Yes.
So are these like decorators or wrappers in Python, these macros?
Not quite. So Julia has a very rich support for complete metaprogramming. So you can essentially write your own language within Julia and have it sort of compile down to something there. We won't really cover the nitty-gritty of metaprogramming here. There's a bit of a section in the notes that goes into it, but you can just think of it as code that writes code. For example, we'll look at a benchmarking thing in a second. So the way we run this code is we initialize, if you look at the bottom left-hand side, we initialize this array numbers just randomly with 32-bit floating point values and 128 of them. And then the way we call the function is just function name, open brackets, a name of the array. And yeah, you get some result out of it. And the same with the SIMD. You don't have to do anything else special. You just add in the macro and it should change the way the code is written for you. Has anyone noticed anything strange about the numbers that come out?
Different loss digits.
Yeah, they're slightly different. So this is just a sort of note, but floating point arithmetic isn't associative at all. So if you do adding together three numbers, A, B, and C, if you add the first two numbers together first and then add C, you usually get a different result to if you were to add the second two numbers together first and then add A. So if you're ever checking whether a sum is like equal to 1 with floating point numbers and you find out it's actually almost 1 but not quite, it's usually floating point arithmetic. So you got to be careful of that in your code.
But why is it not associated?
Because remember we were talking about how floating point numbers are represented in memory, and it's a sort of discrete representation of a continuous value in base 2. So you have rounding errors and things in there.
Oh, okay.
Yeah, it is commutative. So if you do A plus B and B plus A, they'll be the same.
But why is the error on the 5th digit? This is the point. Should it be in the 18th digit?
They can compound on each other as well. So this is adding 128 numbers. So if you only have an error right at the end, it can sort of propagate through. And they're only 32-bit numbers as well. Yeah. Any more questions on that? Okay. So the main reason we do this is it's a lot faster. So if we benchmark these two examples, again, this is using a macro B time. And you can kind of think of B time as just starting a stopwatch before you run your code and stopping it once the code is finished running and then printing out the results. B time is also quite nice because it does a proper benchmark. So it will run your code multiple times and take an average as well. That's why we use this package instead of just the inbuilt tools. You can see here the first one took around 84 nanoseconds, but the SIMD version only took around 7.5 nanoseconds. So it's much, much faster.
Is this SIMD thing unique to Julia, or is this just a general?
No, you can do it in any language. So well, you can do it in any language that supports writing that lower level. So if you're writing in C, for example, you could manually sort of access these instructions and write some source code to sort of manually fill up the registers. If you look at things like NumPy or MATLAB arrays, under the hood, they will have some for loop going through an array to do all the calculations, and they'll probably use SIMD if it's supported on the CPU. So oftentimes you don't interact with these things directly, but in Julia you can. Yes.
Question in the chat.
Okay. Will it already be back? Okay, so the question is, the Julia docs say that unlike Python, you don't need to vectorize your loop. Is that only if we're using the SIMD macro? And it's a good question. No, you basically everything in Julia, a for loop, and using the vectorized version, which means doing an array operation. So if you were to write, like if X was an array and Y was an array and add them together, that would be a vector operation. which is what you would do in NumPy if you've used that previously on MATLAB. And basically the performance rule in Python is try and vectorize as much of your code as possible. But that vectorization just means offloading it to run in C instead of running in Python. That's the main difference between them. Unfortunately, all of the words overlap, but they're not quite the same. And so this sort of low level is like hardware vectorization. Not sure that will answer your question completely, but there is a difference. We'll go into it more next week when we start talking about actual optimization techniques.
Okay, what he says is that regardless if you have vectorized or not vectorized, what you say is that the performance is the same. But what you say here is that this CMD vectorization is a different kind of vectorization, which is lower level.
Yeah, so it's using the CPU calculation. So for example, if you took a CPU that didn't have support for these vectorized code, then that SIMD macro wouldn't change any of the instructions. And that for loop would be the same speed as if you wrote it in C or in a Fortran or whatever.
Okay.
Maybe there might be some slight differences, but yeah, that's all. So yeah, nice thing about the macros is it's 5 characters and you get 11 times faster performance as well. I should note the functions are slightly different. The ones benchmarked here, but I just changed them just to make them easier to read. But essentially they're exactly the same. Okay, that's all we're going to cover for the SIMD part. We'll talk about it a little bit next week as well. But there's not much depth to it other than that first sort of level. Okay, so we'll talk a little bit about what's called the stack and the heap. A lot of you may not have encountered this before because it's a sort of lower level detail that most of the time you don't actually need to worry about. But when we're talking about optimization, it becomes very, very important. So sort of break these down. We'll just talk about stacks in general. And stacks are just a data structure that's used a lot throughout computer science. And if we talk about just like a general stack, it's like a linear data structure. And the way I like to think about it is thinking about like this children's toy. So a lot of you may have seen this in your childhood, but essentially you have a container of items. So this can contain the different colored rings. And the only way you can access rings further down is by accessing them from the top. So for example, if you wanted that second orange ring, you would have to take the top red ring off first before you could access it. So the general rules of a stack is you can only take items off the top, which is called a pop. So you can pop an item off the top, or you can push an item onto the top. You can also like read what the top item is without taking it off as well. And you might think, what's the point of having a data structure that's heavily restricted, but it becomes very useful in a huge array of applications, but particularly in sort of evaluating expressions in a sort of logical, straightforward way. So as an example, I'll just talk about a sort of how you can compute algebraic expressions or evaluate an algebraic expression sort of using the stack data structure. So when we're writing algebra, we can express the addition of 2 variables with just a plus b. This is just one choice of notation you can use, and it's called infix. So you put the operator in between the 2 arguments that it's operating on. Another choice that you have is a prefix notation. So you have the operator on the front and then followed by the 2 arguments. And this is common to what you'll see in like source code in programming. And the one that you may not have seen before is a postfix notation. So postfix, the arguments come first and then it's followed by the operator. And so these are all just choices of how you express your sort of expressions. Computers usually use postfix, and we'll go through an example of why. I should say that this operator takes 2 arguments, so it acts on the 2 to the left of it. So you can have longer expressions as well. So if we take the expression 5x times x plus 2 in brackets minus 1, we can write it out in a postfix notation, and you get this array of characters. And you can see why we don't use postfix ourselves, because it's quite hard to read. There's a pretty straightforward algorithm of how you can convert any infix notation to a postfix. One thing that you will see, there's no brackets in that expression. You don't need brackets in postfix at all. So it sort of simplifies things down. Not for us, for a computer. So we're going to go through a sort of a quick example of how this might be processed by a very simple CPU. So the way this CPU is limited is we have 2 registers, 2 temporary arrays in memory, and we also have an arithmetic logic unit as well, which can do certain computations. So the way we start is we just go left to right on the postfix expression. If we see a number, we're just going to push it onto the stack. And you see the first few steps are quite boring because we're just pushing the numbers onto the stack. Again, imagine x was just any value that you put in, like loaded from some other part of memory. So this stack will fill up until we hit an operator. Now the operator takes 2 arguments and it acts on the 2 objects to the left, which so happen to be the top 2 on the stack. So whenever you hit an operator that has 2 arguments, you pop the top one off the stack and put it into the CPU, pop the next one off the stack into the CPU. You perform the operation, but because you only have 2 registers, you overwrite the first register with the result. So this register gets overwritten to become x plus 2. And then as the final part of this, we store it back onto the stack, or we push it back onto the stack. We just leave register 2 alone. It gets overwritten in a minute anyway. Then we move on to the next operation, and we basically perform the same steps. There are 2 arguments, so we pop the first one into the register, pop the second one into the register, overwriting whatever was there. We perform the addition and store it in the first register, and then push it back onto the stack. And again, move to the next one, and it's the same sort of operation throughout until we get to the final expression that goes back on the stack. So all sort of correct expressions will end up with a single value on the stack right at the end, and that's the evaluated expression.
-1 instead of +1?
Yes, that's a mistake in the yes, it should be -1. Good spot. So yeah, as a sort of you can see why this can be useful when you look at function calls. So it's not just useful for sort of evaluating these semi-complex algebraic expressions, they're very useful in evaluating functions as well. So whenever you call a function, it creates a new stack frame on the overall stack, and a stack frame is just the portion that's used for a single function. There's not too much depth to this, but if you take the example of calculating the factorial of a number, you can define it recursively, right? So the factorial of n is equal to n times the factorial of n minus 1 until you get down to 1, and then it just is defined as 1. So the way you can sort of compute this abstractly with a stack, so yeah, there's your stack frame, is you push the value of n onto the stack. In this diagram, it's going to grow downwards because that's how it's organized in computers usually. And then instead of evaluating the value of the factorial of n minus 1 straight away, you evaluate n minus 1. I've left it out on the diagram here to get 3. And then that creates its own stack frame, which just gets put below the first. And then this will continue until you get to 1. And now for 1, it doesn't call any functions. It just returns the value of 1. So what you can do is push that up into the stack frame, into the third stack frame, and then we add the numbers together, multiply the numbers together as usual. Again out to 6, and then finally combined to 24. So yes.
So instead of growing upwards, why you in your picture the stack growing downwards?
Yeah, imagine it just being flipped upside down. So it grows in one direction, and you keep it in that way. There's a diagram later that hopefully will explain it a little bit better. So yeah, basically, whenever you do a function call like this, if you organize it in the stack way, the result will just be on top, and you can essentially just replace a function call with the result of its sort of stack operations going down and then up. So the main reason why I went into this is it has a very nice advantage, and it's you don't really need to manually keep track of your memory, because all of your variables are local. So that in the intermediate variables we had was like 4, 3, 2, 1. We didn't have to think too much about deciding where they were going to go, and also cleaning up that sort of space in memory afterwards. All we did was grow the stack down and grow the stack up. So every time a piece of memory is not used, all you're doing is moving your stack pointer. So you're saying the stack now ends at this different point instead. The sort of limitations that you have when you use this is anything that you put on the stack has to be known at compile time, because the instructions that sort of move the data around the stack are read-only. They don't change once they've been compiled. And so you must know how big your variables are going to be before you've run your program. And these sort of physical addresses, they're not the sort of absolute place in memory exactly where it is. It's a sort of relative offset based on like where the stack currently is. So yeah, the size can't depend. This says input arguments, I mean like runtime values. So for example, if you ask, if your user asks you to store an array of values and then they give you 10 values, you don't know that it's going to be 10 before the users put that in. So that's the sort of information that you wouldn't be able to put on the stack. Also, the stack has a maximum size. So
which is?
It changes. It's variable based on which language you're using and which sort of computer system you're running as well. So it's also where the stack overflow error comes from, because if you keep calling a function recursively down and down and down, it will exceed this maximum size. So you've overflowed the stack. So that's the origin of the name of that website. Okay, so because of the limitations that we have with the stack, we also have this other sort of data structure that we use to store basically everything else. So the heap is just sort of a large section of memory that you can just use to store any data that you can't really store on the stack. So this is where all of the objects that you don't know the sizes of get put. So arrays, for example, are usually heap allocated. In languages like C, arrays mean statically sized arrays that you have to know at compile time, and so they can be put on the stack. So there's a bit of a complication there, but if we're talking about Julia, arrays live on the heap by default.
Even though I specify the size of the array,
yeah,
lives on the
because arrays are allowed to change size throughout the runtime, so you can extend it and add more items or take more items off. And so at compile time, you don't know whether someone is resizing that array. There is a package that lets you construct static arrays that have extra restrictions on them, so you can't change the size of them once they're created, and they can live on the stack, which again, we'll go into in a lot more detail next week.
Which makes them faster?
Kind of, but probably not for the reason you think. So I'll come on to that in just a second. So when you're using the heap, it's just an area of memory that sort of gets used up as your program is running. So memory is finite, right? You don't have infinite resources. And when you're using an array, it probably won't live for the entirety of your program. And so what you want to do is when you allocate some memory, you want to, well, for one, be able to find a bit of memory that hasn't been used already for another variable. You also want to keep track of which parts of memory are being currently allocated to some variables. And you also want to be able to free up the memory when it's no longer being used. And there are so many different approaches that languages take to handle these problems. And it's all pretty much a choice. But a lot of modern languages, sort of the higher level ones like Python, Julia, MATLAB, C#, JavaScript, the majority of them have what's called a garbage collector, which means throughout your program, you can just ask for memory whenever you want. And it will sort of keep track of which bits of memory you're using or not based on a reference. So inside a function, if you create some memory and assign it to a variable, as soon as you leave that function, that pointer won't exist anymore. And so that memory isn't being used, and the garbage collector can clean that up and make it available for future allocations. We'll talk a lot about that next week. So
why are there languages that don't use garbage collector?
Because it can be it can impact your performance very negatively. So
To have a garbage collector. Okay.
So in order to free up the memory and sort of manage the memory on the heap, oftentimes you need to stop execution and like freeze all of the memory so that the garbage collector can sort of rearrange everything.
Which language don't have?
C, Fortran, like the older ones. Rust. Rust is a newer language, and it has a much sort of nicer approach to this called the borrow checker, which basically enforces some strict rules in your code. There are some operations you can't do, but it ensures that it will manage the memory for you, and you won't sort of leak memory. So it's called a memory leak when you keep allocating and you're not actually using those resources anymore, and the demand for memory of your program just increases and increases until it crashes. Okay. Again, if this is, if you don't understand this to a detail, we will cover it next week as well. Yeah, there's also, I've included a link to a YouTube video that kind of talks about an analogy to this. So you can kind of think of the heap as a very large hotel room, and anytime you check in customers, you have to basically allocate them to a room, and you can't allocate someone to a room that's already taken. And it's like, how do you manage that when the problem size gets really large? Okay, so as a sort of conclusion, this is kind of what your program will look like in memory. So we spoke last time about virtual memory. It's just like a contiguous block of data that lives in RAM. And the first part at the bottom, so the lowest memory address, is where all of your programming instructions will live. So this is the sort of compile time information. They usually won't change during the runtime of your program, especially, well, if you have a compiled program, Julia is slightly different, but there is also a section for the constants in your data as well. They just get baked into the executable memory. Then you have a big section for your heap, which presumably at the start of your program will be completely free of memory and won't have anything allocated. And then sort of right at the top, you have the stack. There's a space between them. And the reason for the space is because it gives space for the stack to grow downwards, and also the heap can grow upwards as well. There are some mechanisms involved so that if the heap grows too big, then you can resize the entire sort of process memory fairly efficiently. But yeah, this is quite a low level detail, but that's pretty much everything.
Who manages this rearrangement?
Usually the operating system.
Oh,
okay. I imagine there's probably a way in a sort of C program to do it manually, but yeah, usually the operating system. Okay, great, that's everything. All I want you to remember from that is there is such a thing as the stack and the heap. Stack is for statically sized objects, and the heap is for variable sized objects.